So last time we learned about capacitance. And then capacitors are composed of two conductors, right? And then if you apply the voltage, electric potential difference between these two conductors, one of the conductor is charged positively and the other conductor is going to charge negatively, so that proportional to the applied voltage, the amount of charge you can store increases. And then this ratio, like the coefficient, is defined as a capacitance. So high capacitance means at the same voltage, the system can store more charges. Okay, so it's more, has more capacity. So how to evaluate this? I gave you like 4 steps. One is you first assign one of the conductor charge Q and the other conductor charge minus Q, right? And then from that, you can evaluate the electric field everywhere, basically, using Coulomb's law or Gauss' law. And once you have an electric field, by taking a integral from one conductor to the other, you can obtain the potential difference. And then potential difference, of course, can be calculated along any path, but you should choose a most convenient path, okay, in order to make your calculation easier. And then once you do that, just taking the ratio of Q and V, you get capacitance. So that's the rule. Okay, so let's apply this rule to this new system, the coaxial cable. I guess most of you already know how to solve this problem, but anyway, I just want to give you just an exercise. So first step, as you remember, assign Q on one conductor, assign minus Q to the other conductor, okay? And then because it's like an infinitely long coaxial cable, coaxial cylinders, you can safely assume that the charge density on conductor 1 and the charge density on conductor 2 are uniform, right? It does not depend on the position. So and then rho 2 can be written as a minus Q divided by what is it, like a 2 pi BL, right? The area, the side area of this conductor. And then similarly, rho 1 is plus Q divided by 2 pi AL, right? It's just a simple calculation. And now you have a charge density on each conductor, and then you can evaluate the electric field due to this conductor. So how to evaluate? Well, you can set your Gauss surface like this, like another cylinder with radius r or radius rho, right? So once you set the cylinder like this, then by Gauss law, d dot ds is equal to d rho 2 pi rho L, and then this is equal to Q, right? The enclosed charge amount. So from this, you know that d rho is Q divided by 2 pi rho L. By the way, regarding the other components like d phi or dz, we learned that we can just ignore this, right? Due to the symmetry argument. I don't want to repeat the same thing here, but like by applying the cylindrical symmetry, the D or E field can only have rho component, and that can only depends on rho, right? And then so D field is given like this. D is equal to like Q divided by 2 pi rho L A rho, right? So you have a D field. So you have a D field means you have E field. So in order to get E field, all you need to do is to divide D by epsilon, right? So you have an E field. So once you have an E field, you can obtain the potential difference between these two surfaces by taking the integration, line integration. So which path do you choose? You want to choose the path along the radial direction, along A rho direction, right? Because E field is parallel to A rho direction. If you take the integral path along A rho direction, it's very convenient, right? So E dot dl from A to B, and then let's say dl is actually A rho d rho. Okay, and then E field has only A rho component, so that product here is just goes away. So this calculation becomes very simple, like A to B, Q divided by 2 pi epsilon rho L, and then d rho, right? Which gives you Q divided by 2 pi epsilon L log of B divided by A. So this is the potential difference between these two surfaces. And now, in order to get the capacitance, all you need to do is to Q divided by V. And because we have V, expression of V as a function of Q, so that you can obtain the capacitance. So if you summarize that, here the capacitance is Q divided by V, which is 2 pi epsilon L divided by log of B divided by A. Okay, so it's easy. So the principle is the same, like assign charge Q and negative Q on each conductor, evaluate the electric field, and then integrate the electric field from one conductor to the other in order to get the electric potential difference, and that's it. And then if you just take the ratio of Q and V, that's capacitance. Okay, so same rule applies here too, right? If you have two concentric spherical conductors of inner radius A and outer radius B, the space between the conductor is filled with the dielectric material of permittivity epsilon. So here you can do the same. I don't want to repeat everything, but like you can write the solution like this. So once you assign charge Q on one conductor, like charge Q on one conductor, and charge minus Q to the other, and then from Gauss' law, because this is very symmetrical system, it's easy to calculate the electric field from Gauss' law. So you can calculate the Gauss' law, and you can obtain the electric field, which is along AR direction, Q divided by 4 pi epsilon R squared, right? Same as the electric field due to a point charge. And once you get that, you can obtain the potential difference by taking the integration, the path integration from one conductor to the other. And then most convenient path is radial path, right? And then if you do it, you get the potential difference. And then taking the ratio with Q, you get the capacitance. Okay? So having capacitance is very easy. Like you can just follow these steps. And in the midterm assignment, one of the problems may have the capacitor problem with like probably non-trivial geometry. So you may have some difficulties in calculating basically E field, right? So in all steps, the only step that is not trivial is obtaining E-field distribution. So in these examples that I gave you, like spheres, cylinders, and plates, it was extremely easy to obtain electric field because you have extremely good symmetry in the system, right? So you can easily apply Gauss law, and then, you know, it's easy. But in some cases, the symmetry is not like good enough. So you may need to think a little more in order to calculate the electric field distribution, right? So that's the only complication in calculating capacitance. And then you will probably see one of the problem that you may need to deal with it in the midterm assignment. Okay, so any questions so far? Anything? Okay. Okay, I guess you are familiar with this thing probably from your undergraduate physics, so you don't have that much of a problem. So here's one question, like series and parallel connections. I guess you already know the answer, but let's look at this, revisit this structure and that structure. So series connection of the capacitors and parallel connection of the capacitors. So in this case, the net capacitance is C1 plus C2. And then in this case, the net capacitor is can be evaluated like this. But do you know why this is the case? Probably you know about this, like probably learn about this in your undergraduate physics, like elementary physics class. But why this is the case? So let's think about this case. This case is easier. Okay. So in this case, here and there, we apply potential V, right? And then we know that in a parallel connection, the potential V is equally applied on both sides, right? So the amount of charge stored in one conductor is Q1, and then amount of charge stored in this conductor is Q2, which is C1V and C2V, right? So as a whole, this system can store Q equals Q1 plus Q2 by applying voltage V, right? So by definition, capacitance is Q1 plus Q2 divided by V, which is Q1 divided by V plus Q2 divided by V. So this is C1 plus C2, right? So we can obtain this relation just from simple definitions. And similar thing can be applied here. We apply the voltage between this port and that port V. And in this case, of course, V1 and V2 are not same as V, right? Instead, V is equal to V1 plus V2, right? And another thing that you can you can know is that here, this is neutral. This entire line is neutral. So if you have charge, say Q1 here, then this one loses that much of a charge. So it has to be minus Q1, right? And then if you have a Q1 here, you automatically have minus Q1 here, and then plus Q1 there. So what you can know from here is that in total, this system can only store, so what we count is the charge stored in this plate and that plate. And what's in the middle is actually, it's not what we are storing. So we are only storing this charge Q1, right? So, okay, so we know that Q1, which is equal to C1 V1, and then this is equal to C2 V2, right? That's what we know. And then another thing we know is that V1 plus V2 is equal to V, right? So combining these relations, what we can achieve is Q divided by, so I'll call Q1 as Q. Q divided by C1 plus Q divided by C2 is V, right? And then dividing everything by Q, you get this. And then this is nothing but 1 over C, just by definition again, right? So this is how you can obtain 1 over C is equal to 1 over C1 plus 1 over C2, okay? From basic rule of V is equal to V1 plus V2. All right, so any question up to this point? Okay, so I will assume that this is what you already knew, so I guess it's not too difficult. But probably the topic that I'm going to talk right now, from now on, is rather new. So it's probably better pay some attention to it. So I will talk about the force in this case. So here we discuss about the work that is required to charge up a capacitor. So we know that per each charge, like in order to move charge from one part to the other, you need to do work VDQ. Okay, so let me show you how it works. So in order to charge up a capacitor, you need to move charge in this plate to this plate, and then this plate to this plate, and so on. And initially, there was no charge stored, so there's no potential difference. In that case, moving charge from one plate to the other is very easy. You don't need to do that much work. But once the large amount of charge has been moved, then it becomes difficult to move one charge to the other plate. And then the work associated with that is actually written like this, VDQ, right? V is the potential difference, and DQ is the amount of charge that you want to move. And then V, of course, changes as a function of Q, right? How much of a charge is stored at the moment. So to get the total energy, you need to integrate VDQ from when charge was 0 to Q, like capital Q, right? By doing this, you can obtain the energy required to make this plate without any charge to this plate with plus Q and minus Q charged, right? And then that energy difference is actually Q squared divided by 2C, or CV squared divided by 2. So this is an energy electrostatic energy associated with capacitor. Okay, you need this much of energy in order to build up this much of a charge. And then here's an exercise. So the situation is like this. You have a length L parallel plate capacitor, and then it's partially filled with a slab of insulator, slab of a dielectric with a relative permittivity epsilon r. And then x is the distance from the end of the capacitor to the end of the dielectric slab. Okay, and then width here, the width of the capacitor is given by W. And then you can also assume there's this dielectric slab can freely move around. So there's no frictional force between the plate and the dielectric slab. Now, so now you don't, you disconnect this capacitor from a battery so that the total amount of charge here, the free charges are same and it doesn't change. So the question is, in this configuration, at which direction this dielectric slab feels force? Is this is it gonna feel the attractive force or repulsive force? That's the question. Like in this configuration, where do you think this dielectric slab is gonna move? Like inside to the inside or to outside? And then I want also you to give me the answer why, the reason why you think so. So can anyone guess? Can you type in and then type in the answer and then just briefly tell me why you think so? Can anyone answer? Can anyone type in which direction it's gonna feel force? Maybe this question is a little bit complicated or a little bit difficult for you to answer. If I just give you okay, some people say to the left, some people say to the right. But why? So let's think about this type of an example. Say you have a heel, okay? And then, of course, if you think about the gravitational potential, here the potential is high. Here potential is low, right? Gravitational potential. And then you place a ball here. Where do you think the ball is gonna move? To the left or to the right? In this case, the ball is gonna move to the right, right? It's a trivial thing if you think in this way, right? So if things feel force to the direction where potential becomes lower, potential energy becomes lower, right? So the F is negative gradient of potential, right? So potential wants to go down, right? And then that's the how the force works. Okay, so now going back to this problem, we know that the energy stored is Q squared divided by 2C, and then Q is constant in this case. And then let's compare two cases where you don't have any insulator in between. That case, we call it as a C0. And then we have the insulator is filled up the entire space. We call this as a C1. Which one is larger? C0 or C1? Can you type in which one is bigger? Like C1 is larger or C0 is larger? Is this difficult question? Can you? Okay, C0 is larger, is what Fakhri said. Is this true? So let's remember how the capacitance of a parallel plate capacitor looks like. C was what? Epsilon A or S divided by D, right? Yes. So when epsilon becomes larger, capacitance goes up, right? So compared to the free space, if you have a materials inside, you have larger capacitance. So C1 is larger than C0, right? In other words, stored energy for the same amount of charge is like this, right? So having the insulator in between the gap has lower potential compared to there's nothing in the gap. So the system wants to move toward that direction. The system wants to have the insulator inside the gap. So the insulator feels the attractive force. So force to the left is the answer. Okay. So if I make this argument a little more rigorous, it becomes like this. You can write the capacitance. You can write the capacitance like this, right? Partially filled with like free space, and partially filled with material. So and then you have epsilon r here. So this is the capacitance of the system. And then W, the work or stored energy, can be written like this using that capacitance. And then force is minus dW dx, right? As I said, in this case, it's just a one-dimensional problem, so it's easy to evaluate. And you can obtain that the direction of force is negative, right? So that means F applies to the direction where X becomes smaller, where X decreases. So it's like an attractive force, right? I hope everyone understands the argument. Okay, so now let's move on to even more interesting problem. So now we have the same problem, but in this case, the capacitor is connected to a battery. Okay, so that battery is held at V, potential V. So in this case, what's constant is not the charge, right? If it's disconnected, then charge cannot move anywhere, so it just stays there. But now it's connected, so what's constant is V instead of Q, right? So just the energy stored in the capacitor is like from our previous example. You should use this equation, CV squared divided by 2. Right? So let me ask you the same question. In which direction this capacitor, this dielectric slab wants to move? To the left or to the right? Everyone says it's to the right. The answer is actually to the left. It's very confusing, right? So everyone says it's to the right, because if you move to the right, your potential energy goes down, right? So that you're happy. So the system wants to move that direction. So that's your argument, right? And that's why what I said in this example. In this example, I exactly said that this slab wants to move to the left, because that way potential energy goes down. Okay, if you apply the same argument in this case, where potential is held constant, things wants to move to the right, and that's a reasonable way to answer it. But in reality, it actually also moved to the left. So what's missing here? That's difficult to know, right? What's missing? The V is not the constant. Well, V is constant. V is constant. You don't question about that. But that's a nice try. But V is constant. Yeah. So as some people pointed out, what we want to minimize is the total energy of the system, right? And then this work here, this is just the energy stored in the capacitor. So, and then now the system is not isolated. So in the previous example, the system was isolated. The system is only composed of the capacitor. So we only take into account capacitor energy. But here we have battery. So battery does also work. So we have to take into account the work done by battery too, and then minimize everything as a whole. So that's how it works. So here, dW dx, as we learned earlier, takes into account the energy associated with the capacitor itself. But that's not the end of the story. Here we have another term, VDQ. So battery here does work to move the charge from one plate to the other, which is VDQ, right? V is held constant, and then Q is the amount of charge moved, and that's what battery does. So if you add them all, and then calculate the net potential, not net energy change, then you will see still this guy wants to move to the left. Okay, so this is one interesting actually exercise that I really like, because it's very counterintuitive in a sense, right? Okay, so that's all I wanted to say for in this chapter.